A 33 billion-ton object moving at over 215,000 kilometers per hour is racing through our solar system, and unlike any comet before, its arrival has triggered a scientific standoff. This is the story behind 3I/Atlas. ESA images reveal shocking truths. European scientists released baffling optical data hinting at physics that no known comet follows, while NASA's limited public findings only deepen the puzzle. Why has this interstellar visitor defied every expectation? From an unprecedented negative polarization reading to coma behavior that makes experts question the very rules of comets. The standard models don't fit, and the stakes are mounting as 3I/Atlas races toward a point of no return. What's really hurtling toward the sun and what secrets are being kept? 58 kilometers per second. That's the measured hyperbolic excess velocity for 3I/Atlas, an interstellar visitor traveling nearly 215,000 kilometers per hour as it slices through the solar system. No comet or asteroid born in our neighborhood can reach such speeds. The sun's gravity simply isn't strong enough to sling a homegrown object onto a trajectory like this. Astronomers knew at once. Only an outsider, ejected from another star system, could arrive with this much momentum to spare. The confirmation came in the numbers. Orbital calculations showed an unbound path, an eccentricity greater than 1, and a velocity that no gravitational pull from the sun could ever reverse. Even before the first images sharpened, the object's speed alone set it apart from every comet catalogued before. This isn't just a fast-moving snowball. This is a fragment of another planetary system, crossing our solar system on a one-way journey. At this velocity, 3I/Atlas covers the distance from Earth to the Moon in just over 2 hours. It will never circle back for a second pass. The window for observation is brief, measured in months. As it hurtles toward perihelion, every day brings it closer to the sun, and closer to the point where its secrets may be lost forever. The urgency is real. For astronomers, this is a race against time to capture data from a fleeting, unrepeatable encounter with the wider galaxy. At a phase angle just over 6 degrees, ground-based polarimeters recorded an extraordinary result. 3I/Atlas's coma reflected sunlight with a minimum polarization of -2.77%, plus or minus 0.1%. That figure stands alone, deeper than any comet or asteroid measured to date, rivaled only by the most extreme trans-Neptunian objects. Negative polarization means the dust grains scatter light in a way that the electric field aligns perpendicular to the scattering plane, a subtle optical fingerprint that reveals the inner structure of the particles themselves. For typical comets, the negative branch bottoms out around -1 to -2%, and always at slightly larger phase angles. Here, the curve is sharper, deeper, and shifted, a sign that the dust in Atlas's coma is not just icy and porous, but built from aggregates of submicron grains, mixed with dark organics and water ice in proportions rarely seen. Laboratory models using high-porosity, icy organic clusters can reproduce this effect, but only under very specific conditions. Monomer sizes much smaller than a wavelength of light, porosity above 90%, and a blend of materials that mimics the surfaces of red centaurs and distant Kuiper belt objects. The measurement, however, hovers near the edge of what ground-based telescopes can reliably extract. Sky background, unresolved coma, and calibration uncertainties all threaten to blur the true depth of the negative branch. Even so, multiple independent teams, using different telescopes and filters, converged on the same deep minimum. No spatial structures were detected, just a smooth, diffuse coma, its light curve and polarization refusing to fit the solar system's template. the numbers force a new question. What kind of dust, forged in another star's nursery, could scatter light in a way never before seen by Earth's instruments? Hubble's sharpest images set an upper limit on the nucleus of 3 Gamma/Atlas, no more than 5.6 kilometers across, with the real size possibly just a fraction of that. Some estimates push it down to 320 meters. The comet's mass, then, remains a moving target. If it's on the larger end, and we use a typical comet density, the maximum mass could approach 46 billion tons. But with so much uncertainty in the size, the actual figure might be orders of magnitude less. The real mystery isn't just the numbers, it's the gap between what telescopes see and what the comet's motion reveals. Despite clear signs of outgassing, jets, a growing coma, there's no measurable non-gravitational acceleration in its orbit. Standard gravitational models fit the trajectory without needing to add any rocket-like push from escaping gas. This leaves astronomers with a puzzle. Either the comet is so massive that even strong jets barely nudge its course, or the outgassing is somehow balanced, canceling out any net thrust. Until new data narrows down the size and mass, the true nature of 3I/Atlas hangs in the balance. Spectrographs from the James Webb Space Telescope revealed a coma unusually rich in carbon dioxide, setting 3I/Atlas apart from most solar system comets, which tend to be dominated by water vapor. The measured carbon dioxide levels are high enough that, even at distances where sunlight is weak, the comet's surface began releasing gas, evidence of volatile ices that sublimate far from the sun. On September 15th, ground-based telescopes tracked a cyanide coma stretching nearly 180,000 kilometers, its shape elongated away from the sun. Meanwhile, the dust tail extended another 100,000 kilometers, with a color trending redder as the comet drew closer. Hints of atomic nickel vapor, detected by the Very Large Telescope, matched concentrations found in solar system comets, but no clear sign of iron appeared in the preliminary spectra. The true extent of the carbon dioxide envelope remains uncertain, as each instrument captures only part of the coma's diffuse veil. With the comet now hidden behind the sun, astronomers are left waiting for post-perihelion data to confirm whether these early chemical signatures hold up under closer scrutiny. The orbital plane of 3I/Atlas sits just 4.89 degrees from the ecliptic, a near match to the flat disk traced by the planets. For an object arriving from the depths of interstellar space, that kind of alignment is rare. Statistically, the chance of a random interstellar arrival coming within 5 degrees of the ecliptic is about 1 in 300. Yet here it is, threading through the solar system almost as if it belongs. The comet's inbound path also passes within 9 degrees of the spot in Sagittarius, where the 1977 WOW radio signal was detected, a coincidence that covers less than 1% of the sky but carries no established physical link. These geometric overlaps invite speculation, but astronomers caution that with enough arrivals and enough possible alignments, odd patterns are bound to appear. What stands out more is the detection rate itself. 3 interstellar objects, Oumuamua, Borisov, and now Atlas, in just 8 years. Improved surveys and sharper algorithms explain much of this uptick, but the numbers still challenge the old idea that such visitors are once-in-a-century events. Each new arrival forces a recalibration of what's truly rare, and what might just be waiting for us to notice. Data pipelines define the pace of discovery. Within days of 3I/Atlas's official announcement, the European Space Agency posted processed images and observing logs from the ExoMars Trace Gas Orbiter's KSSIS camera. These public releases included exposure times, calibration details, and even raw photometric files, enough for outside researchers to rerun their own analyses. In contrast, NASA's main outputs for the same window focused on orbital elements and ground-based tracking updates, with no immediate release of Mars orbiter or test datasets. Hubble and JWST observations, scheduled as target of opportunity events, followed a staggered release policy, with embargoes lifting as principal investigators completed their first round of analysis. The result? A patchwork of access, where open data let some teams publish rapid-fire results, while others waited for embargoed files. As perihelion approaches, the flow of information will shape what the scientific community can watch and what questions remain out of reach. October 30th, 2025. That's the date circled on every astronomer's calendar. As 3I/Atlas swings closest to the Sun, global telescopes will be watching for signs that could rewrite the rules of comet science. Fragmentation is the first thing to track. If the nucleus breaks apart, it could reveal internal layering or hidden weaknesses, much like Borisov's shattering in 2019. A sudden flare in brightness would hint at volatile ices vaporizing under solar heat, while a steady coma could signal rare stability for an interstellar wanderer. Spectrographs will be hunting for changes in gas composition, especially shifts in carbon dioxide, water, or cyanide levels, as the comet's chemistry responds to rising temperatures. Precise position tracking may catch the faintest orbital wobble, exposing hidden jets or confirming a massive, dense core. Each of these signatures is testable, falsifiable, and visible to anyone with the right tools. The verdict will come in real time. In October 2025, 3I/Atlas will reach perihelion after crossing the solar system at an estimated 215,000 kilometers per hour, confirmed by ESA's published trajectory data. The object's reported deep negative polarization, measured at approximately -2.77% near a 6-degree phase angle, stands as a rare optical anomaly among comets and asteroids. Yet, despite multiple agencies releasing raw images and spectra, key questions remain. The true mass, precise chemical makeup, and the cause of its minimal non-gravitational acceleration are still under active investigation, with some measurements awaiting independent confirmation. Not all data, especially from NASA's Mars window, has been made public, highlighting ongoing barriers to open scientific analysis. As perihelion approaches, astronomers worldwide will watch for sudden fragmentation, unexpected activity, or signs that challenge existing comet models. The evidence so far shows that 3I/Atlas does not fit neatly into known categories, and its passage may force revisions to how scientists understand both interstellar objects and cometary physics. What we know is remarkable. What remains hidden could be more so.